Greetings, students. Welcome to another lesson from iCampSA. This will be on differential calculus. Okay, so what is calculus? Calculus is a branch of mathematics that deals with gradients of curves or graphs, and in particular that is what we call differential calculus. So calculus has two branches. It's the differential calculus that I just highlighted, and also there's another part which is integral calculus, which deals with the area under the curve. So that is beyond the scope of this course. Here we're only going to be focusing on differential calculus. Okay, so as I've already mentioned that differential calculus deals with the gradients of curves and graphs. From the function, we generally have the average gradient between 2 points. We have the average gradient between 2 points, which is basically the difference of the height over the difference of the run. And this is the formula that we use to calculate the average gradient. You may be familiar with it as maybe m is equal to y2 minus y1 over x2 minus x1. So it's basically the difference of the height over the difference of the run. So this is the formula that we use to calculate the gradient between 2 points, or the average gradient between 2 points. So let's quickly do an example of calculating this average gradient between 2 points. So for example 1, we are given that function of f at x is equal to x squared minus 2x plus 2, and we are asked to calculate the gradient between x is equal to 2 and x is equal to 4. So first thing first, we need to find the corresponding y values for these x values, and in order to do that, we have to take the function that we are given. We have f at x, let's say f at 2 is equal to 2 squared minus 2 into 2 plus 2. This will be equal to 2 squared is 4 minus 2 times 2 is 4, so that should be 0. So we'll be left with 2, and then for f at 4, we're gonna have 4 squared minus 2 times 4 plus 2. So we have 4 squared is 16 minus 2 times 4, which is 8. Therefore that would be 8 plus 2, which is 10. So now we have the corresponding y value. So in order to calculate the average gradient, we're gonna say average gradient. We have the average gradient, which is the difference of the height over the difference of the run. So let's take f at 4 as our y2, which is 10, minus f at 2, which is 2, over x2, which is 4 in this case, minus x1, which is 2. Therefore we're going to have 10 minus 2 is 8, and 4 minus 2 is 2. Therefore this will be equal to 4. This will be our average gradient. So that's how we basically calculate the average gradient. Okay, between 2 points, by the way, between 2 points. But now what if we want to estimate the gradient at just a single point? Let's say we are given a curve. Maybe I can draw the curve here. Let's say we are given a curve, maybe a curve of this nature, a parabola, just a simple curve, and we want to estimate the gradient of the curve at just a single point, So if we want to do that, now we have to employ other methods, but the idea is the same. We are still looking we're still gonna build on top of the average gradient thought process, if I may say, So to calculate the gradient or to estimate the gradient of a curve at a single point, at just that single point of contact, what do? We estimate it by finding the point on the curve closest to the point of interest. Let's say we have this point here. We want to estimate the gradient at that point. I call it f at 1. So what we have to do, we first have to find another point on a curve, closest to the point of interest, to the point where we want to find the gradient. Say we want to find the gradient at this point here. First step is to find another point on the curve, this curve, the parabola that we have in this case, and then yes, a point closest to that point of interest, and then we have to calculate now the average gradient between the 2 points, the point closest and the point of interest. So let's say we have this point occurred. This is our x values. I forgot to label this, and this is our y values. Okay, what is happening here? We have that point that I marked that we want to estimate or to find the gradient at the point where x is equal to 1, just at that point, not the average gradient, just the gradient at that point. I said the first step is to find another point on the curve that is closest to the point where we want to find the gradient of the curve, or the gradient of the tangent, if I may say. Okay, so we have that point where x is equal to 1, and we have the second point where x is now equal to 1 plus the h. And the h, what is the h now? The h that we just added here is the horizontal distance, between the 2 points, the point of interest and the point closest to the point of interest. So h is just that distance between those 2 points. Okay, so what do we have here? We have f at 1, which 1 and 1, remember that 1 is our point. We are looking to calculate the gradient at the point where x is equal to 1. Okay, let's calculate the average gradient between these 2 points. Remember, gradient at a point is estimated by finding a point on the curve closest to the point of interest, and then calculate the average gradient between the two. Let's just calculate that for now, the average gradient. So the average gradient, remember, it is the difference of the heights over the difference of the run. Okay, let's go ahead and do that. So for the average gradient, we're gonna have y2, of which in this case will be f at 1 plus h, minus f at 1 minus f at 1 over 1 plus h minus 1. Okay, let's say I forgot to mention something here. Let's say this function of f, let's say is the simple what you call this thing, parabolic function, which is f at x is equal to x squared. Just a simple parabolic function, and we are given f at 1 and f at 1 plus h. So we need to find the corresponding f at 1. We are given the x is equal to 1 and x is equal to 1 plus h. So we have to find the corresponding f at 1 and f at 1 plus h. So our function is what? Our function is f at x is equal to x squared. Let's find f at 1. F at 1 will be 1 squared, which is 1, and then f at 1 plus h will be 1 plus h squared. Therefore, this will be 1 squared will be 1 plus 2h. 1 times h times 2 will be 2h plus h squared. And then let's substitute the values. Let's substitute f at 1 plus h will be 1 plus 2h plus h squared, minus f at 1 is just 1 over 1 plus h minus h, minus 1 plus h minus 1. This will cancel this and this will cancel this, and therefore we will be left with 2h 2h plus h squared over h. Let's take out the common factor on the top part, so we're gonna have h into 2 plus h over h, and then the h in the numerator and the denominator will cancel, leaving us with 2 plus h. And this is the average gradient. This is the average gradient between the 2 points, f at 1 plus h and f at 1. And another important thing to note here is that h can never be equal to 0. Let me put this in writing. H can never be equal to 0. And the reason is what? H is in the denominator. Since yes, as you can see that h there is in the denominator. So if h become 0, then this will be an undefined function, So since h is in the denominator on the original function, it can never be equal to 0. Let's put that in writing. H is the denominator. On the original function. So it can never be equal to 1. Okay, it can never be equal to 1. And then remember that h is the horizontal distance between the 2 points. The points that we are using to calculate the average gradient between the 2 points on the curve. Okay, and then from there, another concept is now introduced. If we were to take smaller and smaller values of h, of h, that means we will move closer and closer towards finding the gradient at that point. We'll be moving closer and closer to finding the gradient at that point. As you can see here, by taking smaller and smaller values of h, the horizontal distance between the 2 points, the closer we move towards finding the gradient at the point. And this is what we call the limit concept. It's the limit concept which is used to express the idea that I've just talked about, the idea of taking smaller and smaller values of h. So we use the limit concept to express that, because when we take smaller and smaller values of h, when we are moving, so in other words, we are taking points closer and closer to the point of interest here, to the point where we want to calculate the gradient. So we are moving closer and closer to that point by taking smaller and smaller values of h. Let's say, for instance, we were to cut the h in half here. That means the point will now be here. The new point will be here on the curve if we were to cut the h distance in half, So this will be our line now, that will be our line between the 2 points. We'll use those points to calculate the average gradient. So by taking smaller and smaller values of h, we are moving closer and closer towards getting or finding the gradient or the accurate gradient at a point. And then this is what we call the limit symbol. And here the limit concept, here we have the symbol of the limit concept. So we have lim and a as h approaches 0, or the limit of a function as h approaches 0, and that h error 0 represents that h approaches 0, but h can never be equal to 0. Remember why? Because h on the original function was in the denominator. So if h becomes 0, then our function will be undefined. Okay, so let's say for example 2, we are given this function. Now we are asked to calculate the gradient between, or the average gradient between x is equal to 3 and x is equal to 3 plus h. And then for b, we're asked to determine the gradient of a tangent to f at x is equal to 3. You see now what's happening? We're asked to find the gradient at just that point, which is 3. Now we're gonna employ what? The limit concept. So we're gonna move h closer and closer to 0. But first, let's calculate the gradient. So we are given that function, which is f at x is equal to 2x squared minus 3. So first thing first, when we are calculating the gradient, we need to find the corresponding y values. We already have the x values, which is x is equal to 3 and x is equal to 3 plus h. So let's go ahead and calculate the corresponding y values. So f at 3 will be 2 times 3 squared minus 3, and then we're gonna have 3 squared is 9 times 2 is 18 minus 3 will be 15. Yes. 3 squared is 9 times 2 is 18 minus 3 is 15. Yes. Okay, and then let's go ahead and find the corresponding y value for f at 3 plus h. We're gonna have 2 into 3 plus h squared minus 3. This would be equal to 2 into 3 squared is 9 plus 6h. 9 plus 6h plus h squared minus 3. Therefore, we're gonna have 2 times 9 is 18. 2 times 9 is 18 minus 3 will be 15 again. And then 2 times 6h will be plus 12h plus 2h squared. Okay, now we have the corresponding y values for x is equal to 3 and x is equal to 3 plus h. Okay, so the next step is to do what? Is to find the average gradient. That's what we were asked to determine. So for the average gradient will be equal to f at x plus h minus f at x over x plus h. I'll just say x plus h minus x minus x. Yeah, I should have just used what you call this thing. They give an x value, which is 3. Actually, f at 3 plus h, 3 and 3 plus h. It just makes things simple. Okay, now let's substitute what we have there for the corresponding y value. We have 15 plus 12, 15 plus 12h plus 2h squared minus 15, where f is equal to 3, where x is equal to 3, and then we have 3 plus h minus 3, and as we can see that this 15 will cancel, this 3 will cancel with this 3. We're gonna have now 12h plus 2h squared. Let's take out the common factor of h. Will be left with 12 plus 2h over h, and then the h in the denominator will cancel the h in the numerator, so we'll be left with 12 plus 2h, and this is the average gradient between these 2 points on the curve. The average gradient between these 2 points on the curve. Okay, and then the following question go ask you to determine the gradient of the curve, the gradient of a tangent, to f, to this function at x is equal to 3, at x is equal to 3. Okay, so I said to find that this will be our b, we now have to take the limits. So for b, the gradient of f will be equal to the limit as h approaches 0 of this gradient that we have here. That is how we go about calculating the gradient of f at x is equal to 3, and then we now substitute the h with 0. 2 times 0 Therefore the gradient will be 12. Okay, so that is how we calculate the gradient of f as at x is equal to 3. Basically, we're gonna take smaller and smaller values up until h is equal to 0, but h can never be equal to 0 in principle, because that will make the original function to be undefined. Okay, next. So the gradient of a tangent to any function f at a point, just any point, so I just used x is equal to a, will be given by this formula, or is defined by this formula, So if we are looking to calculate the gradient of a tangent at any point in the function, we can just use the limit formula that we have here. Lim as h approaches 0 is equal to f at a plus h, and a is that point, that x value, that x value, minus f at a is that x value, just over h. Because what you will notice here, as we keep on calculating the average gradient, always in the denominator will be left with what? Will be left with h. We'll be left with the difference with the distance between the 2 points, which is h. So we can just simplify that by as it is shown here by the formula for the limit. Okay, so yeah, and here is just a graphical representation of what I was mentioning there. So what do we have here? We just have this simple curve. We have at x, we have the x values. This is x values and these are y values. So we have a, just it can be any x value, and then the distance from a to the new point would be a plus h. This is our h, that distance from a to h, and then we have the corresponding y values. Okay, let's quickly do this other example here. Example number 3, we are asked to calculate the average gradient between x is equal to 0 and x is equal to 5. You already know, first thing first, we have to find the corresponding y values. So f at 0 is equal to 0 squared minus 1, which would be equal to -1, will be equal to -1, and then f at 5 will be equal to 5 squared minus 1. 5 squared will be 25 minus 1, we will have 24. And then for average gradient, just gonna say average gradient will be equal to, remember, we're gonna have f at x, which is f at 5 in this case, f at 5. Okay, f at 5 minus f at 0 over 5 minus 0 over 5 minus 0. Yes, 5 minus 0. Those are the x values that were given here. So f at 5 is 24 minus 1, which is 23, over 5. This is equal to 24 minus that is 25 over 5. Since 24 minus would be 24 plus 1, basically this would be equal to 5. That will be the average gradient between those 2 points for the function that we were given there. Okay, and then next we are asked to determine the limits of that function. So given f at x is equal to x squared minus 3x, we are asked to find the limits, okay, between 2 and 2 plus h, between those 2 points. Okay, so first thing first, we need to find the corresponding values for what? For f at 2 and f at 2 plus h. So let's go ahead and do that. the corresponding values. So f at 2 plus h, let's start with f at 2 plus h, would be equal to 2 plus h squared minus, wherever we see x, we put now 2 plus h again. So therefore we gonna have 2, it will be 4, it will be 4 plus 2 times h will be 4h plus h squared minus 6 minus 3h minus 6 minus 3h. Okay, this would be equal to 4 minus 6 would be negative 2, so we're going to have h squared 4h minus 3h will be h, so therefore plus h minus 2. Yeah, I think we're gonna have that. And then let me move this one a bit to this side. Let's calculate f at 2, which is gonna be 2 squared minus 3 times 2. Basically we're gonna have 2 squared will be 4 minus 6. 4 minus 6 will be negative 2. Okay, now we have that. Let me move this one a little bit down here. Okay, so the next step, let's determine the limits between these 2 points. Okay, between these 2 points, we have already evaluated f at 2 plus h and then f at 2. So next step, we simply just come here and say this will be equal to, or we can say lim as h approaches 0 of f2 plus h minus f at 2 over h is equal to the limit as h approaches 0, what is f at 2 plus h will be h squared plus h minus 2, and then f at 2 would be minus 2 over h. So let's say the limits as h approaches 0. So basically here that negative 2 and positive 2 will cancel. We'll be left with h squared plus h. Let's take out h as a common factor, therefore we'll be left with h plus 1 over h. The h in the numerator will cancel the h in the denominator, and then next we'll be left with lim as h approaches 0 is h plus 1, and then we basically equate h to 0, therefore this will be equal to 1, that's the yes, that's the limits as h approaches 0. Okay, yeah, next let's quickly do another example again. So we are also find the lim as h approaches 0 between these 2 points, 3 plus h and 3, 3 plus h and 3. So first thing first, let's find the corresponding values for f at 3 plus h and f at 3. So f at 3 plus h for that given function there, we're going to have negative 3 plus h squared plus 3 plus h will be, we're going to have 3 squared will be 9, 3 times 2 is 6 plus 6h plus h squared plus 3 plus h. So we're gonna have negative 9. Okay, so negative 9 plus 3 will be negative 6, basically negative 6, and then negative 6h plus h will be negative 5h minus h squared, yeah. Hopefully I didn't make a mistake there. I don't think so. Let's calculate f at 3, which would be equal to minus 3 squared plus 3. Then we're gonna have what is this? 3 squared is 9. We're gonna have negative 9 plus 3, which basically is gonna be negative 6. Okay, now we have those two. Let's find the limb. So the limit as h approaches 0 between f at 3 plus h minus f at 3 over h is equal to lim. So remember never to drop this symbol of lim as h as h approach the limits as h approaches 0 right up until you substitute the h with 0. You don't drop it, always remember to write it. So what is f at 3 plus h is what? Is negative 6. It's negative 6 minus 5h minus h squared, and f at 3 is negative 6. So minus 6 over h. Therefore we're gonna have lim as h approaches 0 minus 6 plus 6, this and this will cancel, will be left with negative h, negative 5h and negative h squared. Let's take out an h as a common factor, so we're gonna have h into negative 5 minus h over h, and then the h in the denominator and the numerator will cancel. Therefore we're gonna have lim, let me write here, lim as h approaches 0 negative 5 minus h, of which will be equal to minus 5 minus 0 will be equal to negative 5. So basically that's the gradient at the point or at 5, where x is equal to 3, not 5, where x is equal to 3. Okay, so that is how basically we determine the derivative, the limit, as h approaches 0, or the gradient at a single point. Okay, and then next we have the derivatives. So what we were doing here is a little bit longer way, determining the gradient from first principles, or by using the limits, is a little bit longer way. There are shortcuts, of which is what we are going to be introducing right now, which are called the derivatives. Shortcuts for determining derivatives. So what is a derivative basically, before we get started? So a derivative is a function that gives the gradient of a tangent at any point on a given function. So a derivative on itself is a function, hence why it allows us to determine what? The tangent. Okay, let's say just for what you call this thing, for argument's sake, let's say we have a function which is a parabola, like this. We can determine the derivative of this function. Maybe it's gonna be a straight line like this. A straight line. We mean to make it, or to write on top of that, a derivative of that function. Let's say maybe we have your x and y values like that. Okay, so what will happen? This derivative, this function here, this straight line function here, which we call what? A derivative, will allow us to determine the gradient at any point. If we were to select any point here on the original function, that parabola there, and once we have the derivative, we can determine the gradient, of the original function at any point of the given function. Okay, so here what do we have is a symbol, or maybe since it didn't take any space, this is the symbol of the of the derivative here, f prime x, or f prime. In short, that's the symbol of the derivative. So f prime x is actually equal to the lim as h approaches 0 of f at x plus h minus f at x over h, so it's also equal to that, or it's basically equal to that. So f prime x. All right, before we move any further, let's do this quick example. So we are still doing determining the derivatives from first principle. So whenever we're determining the derivative from first principle, we are basically using the limits. We are using the limit concepts. We are using the limit concepts. You will see once we get started with the derivatives. Okay, so we're given that function of f at x is equal to x squared plus 1, and we are asked to determine or to find the derivative from first principle by using the limit concept basically. So first thing first, we have to determine f at x and then f at x plus h. So f at x we are already given for number 1. F at x, let me see something. Okay, for number 1, so f at x, let me do it like this. From first principles, just add a page for this one. Let's determine from first principle the derivative of this function. So what do we have? We have f at x, which is equal to x squared plus 1, and then next what do we have? Let's find f at x plus h. F at x plus h, that shortest distance between the 2 points, between x and whatever there, and the point closest to the point of interest, our x in this case. So f at x plus h will be x plus h squared plus 1. This would be equal to, let's expand, we're gonna have x squared plus x times h, 2xh. Gonna have 2xh plus h squared plus 1. Okay, basically that is f at x plus h. Let's find now the derivative of this function, f prime x. F prime x, we said from the formula, is equal to what? Is equal to lim as h approaches 0 f at x plus h minus f at x over h. Okay, therefore let's now substitute lim as h approaches 0. F at x plus h is equal to what? Is x squared plus 2xh plus h squared plus 1 minus f at x is what? Is x squared. So it's gonna be minus x squared minus 1 over h, and then let's cancel the like terms. X squared and x squared will cancel, 1 and negative 1 would cancel, so therefore we'll be left with lim as h approaches 0 of 2xh plus h squared over h. Let me quickly add a page here. Add a page. Okay, and then we can move this one a little bit lower again onto the new page. Okay, now let's come here. We have 2xh plus x, therefore we're gonna have lim as h approaches 0. Let's take out the common factor, which is h, will be left with 2x plus h over h, then the h will cancel, therefore this one will be equal to lim as h is equal to 0 of 2x plus h, and then now we can substitute the h for 0. Therefore we're gonna have 2x plus 0, which is equal to 2x, and that is the derivative of this function x squared plus 1 from the first principle. Okay, and then the second example. Okay, for this example we are dealing with a fraction. So whenever we are dealing with a fraction, an expression that is given as a fraction, or maybe in other cases when the expression is given as a what, as when the variable is under maybe a root sign, we first need to change it to write it in what I would just say a linear form, whereby the variable is also on the numerator, and we use the laws of exponents to do that. We use the laws of exponent. So what I mean by that, first f at x, we have to rewrite it as what, as minus 4. This is equal to x. Okay, let me see, something will be x minus 1. No, okay, I think I'm getting ahead of myself with this one. Yeah, I think it's necessary when we are what you call this thing, once we are using the power rule to derive. For now, let's just when we are using the power rule, for now let's just use let's just determine the derivative from the first principle, just the same way we did here. First, by determining f at x, we already have negative 4 over x, and then f at x plus h, f at x plus h is equal to negative 4 over x plus h over x plus h. Okay, and then once we are here, the next step is to go to our formula. Now the next step is to go to our formula. Yeah, so here what we have to do is to find the common denominator. Let's deal with the numerator first. Okay, why am I even using the red pen? So the limit as h approaches 0 of negative 4 over x plus h, minus would be positive 4 over x plus h. Okay, all of this we multiply by 1 over h. Yeah, this just for the numerator. Can even introduce the brackets here, not to, so that we don't confuse ourselves. So the limit as h approaches 0, let's find the common denominator there to combine the fractions. So we're gonna have x into x plus h, that will be our common denominator, and then x into x plus h divided by the first denominator will be left with minus 4x plus 4x plus 4h. I just expanded that fraction, multiplied by 1 over h. So the lim as h approaches 0, minus 4x plus 4x will cancel, and then we're gonna have what, 4 will be left with 4h in the numerator. Gonna be left with 4h into x plus for h over x to x plus h multiplied by 1 over h. So basically this h in the numerator will cancel with this h. Therefore the lim now, as h approaches 0, of 4 over x into x plus h. Okay, so once we are here, we're now only left with 1h. We can basically substitute the h for 0. So therefore we're gonna have 4 over x into x plus 0, of which would be equal to 4 over x squared. And this is the derivative of the function of negative 4 over x, negative 4 over x. Okay, that is that. That is us. Let's go ahead to differentiation. So differentiation is basically the act of finding the derivative of a function. It's finding the derivative of the function. Yes, we call it differentiation. Hence why this is called the differential calculus. So with differentiation, there are a few rules that we're going to introduce. Is now we are not deriving or differentiating from the first principle, so we're just gonna use some few rules, the shortcuts I was talking about, to find the derivatives of a function. So we have the following notations. I should have said notations. For the derivatives, first thing first, we have the one of f prime x. We are familiar with that, also represent the derivative. We have dy over dx, which is basically the difference of the heights over the difference of the run. That is another notation of the that we use when differentiating. So the first one, we simply say this is a derivative of a function of f at x. Derivative, this is the derivative of a function of f at x, derivative of a function of f at x. And then here is the derivative of y with respect to x, derivative of y with respect to x. So this is the derivative of y with respect to x, with respect to x. And then we have capital letter dx when we're deriving like a expression. So this notation, I can try to squeeze this in here, is a derivative of an expression, derivative of an expression, particular expression with multiple terms. Let's say maybe you have x squared plus 2x plus, so we generally use that notation, that last notation here. Okay, so next we have the rules of differentiation. The rules of differentiation, we have rule number 1, which we call the power rule. So the power rule is basically straightforward. What happens here, we take the exponent of the variable. Remember, the exponent of the variable, not the exponent of a or the coefficient, but the variable that we are dealing with. We multiply the whole expression with the exponent, as you can see here, and then we subtract 1 from the exponent. So that is basically how the power rule works. How the power rule works. We take the exponent, we multiply the expression with the exponent, and then we subtract 1. from the exponent. Okay, and then next, let's say we don't have an exponent. Our variable is just like this, so here is not that we don't have an exponent, but the exponent is basically 1. When the exponent is basically 1, that means we take 1, we multiply the coefficient, which is a, and then we subtract 1. So therefore we're going to have x to the power of 0, of which is equal to 1. So basically, when our variable have an exponent of 1, we're just going to be left with the coefficient, which is in this case the a. And then when we just have a constant, we don't have a variable, we are deriving or differentiating this expression with respect to x, but we only have a constant of a. What happens there? The derivative of a constant is always equal to 0. We can put that in writing maybe and say derivative of a constant, the derivative of a constant is always equal to 0. So basically, that is how the power rule works. And another thing to take note of, if there is a variable, if the variable is in the denominator or under a root sign, I think I've already mentioned that. If there is a variable in the denominator or under a root sign, we must first rewrite the expression using the laws of exponent to this form of x to the power of n before we differentiate, of which is what I wanted to do here. But then I remembered that we are deriving from the first principles. When deriving from the first principle, it's not really necessary to rewrite it, but once we are differentiating using the the power rule, or these rules of differentiating, is always important to have your expression in this form here that we have. In this form, I'll just call it a linear expression. It's not necessarily a linear expression, but yeah, for argument's sake, let's just call it in a linear form, whereby you don't have fractions. You don't have your variables under the root sign, And then rule number 2 is the sum and difference rule. Let's say you are differentiating an expression, or multiple expression. Basically, you're gonna differentiate each expression individually. You're gonna differentiate each expression individually. Let's say you have the function of f at x plus or minus the function of g at x, and you are asked to differentiate both of those functions with respect to what? With respect to x. What you're gonna do is you're gonna differentiate the function of f at x with respect to x individually, and then you're gonna also differentiate the function of g at x with respect to x individually. And another thing to note here is that the complex expressions must be simplified until they have no brackets and they have no algebraic fractions. I've already mentioned that. And then until they have no roots of algebraic expressions. They have no roots of algebraic expression. It's always important to simplify your expression before you differentiate. And another important thing to note of, if let's say in your expression you have multiple variables, you have maybe mx squared plus px plus 5, and you are asked to differentiate that expression, also find the derivative of that function with respect to x. the m and the p are treated as what? As constant. Maybe I can quickly write what I mean here, what I'm trying to say. Let's say you are given an expression which is mx squared plus px plus 3. These m and p are treated as constant, or are considered to be constants. Constants, you know. The only thing that is a variable here is the x, you know, that we are differentiating with respect to, you know, with respect to. Okay, yeah, let's quickly do the examples. Let's quickly do the following examples, you know, to show what we are talking about. Okay, so example number 1, for point A, we are to determine the derivative of that expression, which is dx 3x squared. So the derivative here, we just have a simple expression, is gonna be let's use the power rule, take the exponent to multiply the expression. So we're gonna have 6x, and then we subtract 1 from the exponent, so we're gonna have 6x to the power of 1. So it's just gonna be like this. And then for p, let's find the derivative of f at x is equal to 2x cubed. So f prime x would be equal to 3 times 2 is what? 6, and then 3 minus 1 will be 2. That is our derivative for that function. Okay, then let's derive the following expression. Let's determine dy dx for number C. So we are also determine dy dx. Okay, so and we are given y is equal to x to the power of 4. So dy dx will be equal to, we use the power rule again, exponent multiply the expression, we're gonna have 4x, and then 4 minus 1 will be 3. Okay, that is our C. And then for D, we are deriving a constant, you know, so we basically have D, our expression is 12 dx. Always remember that derivative of a constant is what? Is 0. That was straightforward. Okay, so next, we're still in example number 5. For us to find the derivative of the function of f at x is equal to x squared over 3x to the power of 5 over 3x to the power of 5. First thing first, we need to simplify until we don't have the variables in the denominator. So here we have x squared over 3x to the power of 5. The most simple way, let's start by we have x squared over 3x to the power of 5. So I see here we're gonna have 1 over 3x to the power of 3, because remember that x squared is like x times x, and then x to the power of 5 is x times x times x times x, yeah, up to 5 times. So yeah, first thing first, that is what we gonna have there. And then next, we can basically rewrite or remove the variable from there. We can remove the variable from the, what to call this thing, from the denominator. Let's remove the variable from the denominator. So we're gonna have 1 over 3 multiplied by x to the power of negative 3. Okay, and then once we are here, we can now differentiate. So yes, we can differentiate this thing using the power rule. We're gonna have take the numerator multiply the coefficient, so take the exponent multiply the expression. We're gonna have negative 3 over 3, which would be 1, negative 1. This is gonna be negative x, and then minus 3 minus 2 will be minus 1, sorry, will be minus 4. That will be the derivative for this function. Yeah, that will be the derivative for this function. Yeah, basically once you are here, you are done differentiating that. Okay, next let's differentiate this expression with respect to x, deriving y with respect to x. Okay, so we are given, what is this thing? It's a little bit complicated, but it's okay. We are given y is equal to x squared. Remember the sum and difference rule. That's we're gonna be differentiating these functions individually. 2 over 3 over x root x cubed. Yeah, okay, let me move this one a little bit lower. First thing first, we start by simplifying this and removing the variables from the denominator. So y is equal to x cubed, this one is no rearranging, minus 5 times x to the power of negative 2 plus 2 over 3 multiplied by, let's rearrange that. First thing first, we're gonna have x to the power of negative 1 over 3. Yeah, I think it's gonna be 1 over 3, because when we are changing a square root, remember when we have this is the same as x to the power of 1 over 2, and then when we want to move it from the denominator to the numerator, we must change the sign of the exponent to that negative. Yeah, to that negative. Okay, now that we have rearranged this function, we can now go ahead and differentiate or derive this function, with respect to x. So therefore dy dx is equal to, remember the sum and the difference rule, we treat each term or each term basically separately, so x cubed will be 3x squared minus 5 times negative 5 times negative 2 would be positive, actually positive 10, minus 2 minus 1 would be negative 3, plus 2 over 3 multiplied by negative 1 over 3 would be negative 2 over 3 times 3 is 9 x, and then minus 1 over 3 minus 1 over 3 minus 1 will be basically, therefore dy dx is equal to 3x squared plus 10 x to the power of negative 3 minus 2 over 9 x to the power, what is negative 1 over 3 minus 1, we're gonna have negative, it's all gonna be over 3 1 negative 1 minus 3 will be 4. Yeah, it will be 4. Okay, yeah, basically once we are here, we are done. Okay, and then next we are asked to determine to find the derivative of this function. F of x is equal to 4x squared minus 9 over 2x minus 3. First thing first, we are seeing variables. We're seeing the x in the denominator. So we first have to start by simplifying this function before we can start determining or start differentiating the function. Okay, so now we're going back to simplifying. So from just glancing at the numerator, we can see that we have what? A difference of 2 squares. So we have a difference of 2 squares, which is 2x and 3. So basically these two can be written as what? As 2x squared minus 3 squared, difference of 2 squares. And we know how to factorize the difference of 2 squares. I'll just let me write it here. It's okay. Let's factorize the difference of 2 squares. We're going to have 2x minus 3 into 2x plus 3 over 2x minus 3. Let me add a page. Okay, now that we have added the page, let's cancel this one. We'll cancel that one. Therefore, f of x is equal to 2x plus 3. Now we can find the derivative of this function, which is f prime x is equal to 2, basically will be equal to 2. Yes, because 2x we have 1 multiplied by 2. Okay, and then a derivative of a constant that 3 is 0. So the derivative of this function is 2. Okay, so next from there, okay, so that is what we have in terms of differentiation. Now let's go to tangents. To tangents. Okay, to tangents. Remember that when we are deriving or differentiating and we are looking for the gradient of the curve at a point, we are essentially calculating the gradient of a tangent, of a tangent to that curve, hence why we're now talking about the tangent. So derivatives can be used to find the gradient to a graph, to find the gradient of a graph, at any point. To find the gradient of a tangent, something is missing here. I can see derivative can be used to find the gradient of the tangent to a graph, Derivative can be used to find the gradient of the tangent tangent to a graph at any point. Yes, the tangent to the graph at any point. And I'm saying, remember what we had here, or what we were talking about just right now. If you have your function like this one here, then let's just say it's an exponential function, and we want to find the gradient of this function or of this graph at that point here. What I'm saying is we are essentially calculating the gradient of the tangent to that graph there, because remember that the tangent and the curve, they only touch at exactly one point. A tangent and a curve, they will only touch at exactly one point. So the gradient of the curve at that point and the gradient of the tangent will be the same, basically. So if we can find the tangent So if we can find the gradient of the curve, that means we also have the gradient of what? Of the tangent to a graph. Okay, now let's come here. Remember that the derivative of a curve, that f prime x is also used to determine what? The gradient of a curve. So let me see if that was mentioned. Differentiation. Yes, so we said the derivative of a function that gives is a function that gives the gradient of the tangent at any point, so it gives the gradient of the curve at any point, and I'm saying that at that point where the gradient where the tangent and the curve meet, their gradients are equal at that point where they meet. The gradient of the curve and the gradient of the tangent are equal. Hence why I'm saying hence why it is said that derivatives can be used to find the gradient of the tangent to a graph at any point, so we know the equation for a straight line is y is equal to mx plus c, with m being the gradient, so that means we can now use the derivative f prime, at any point that a represents just any point, to find the gradient of the tangent, so the equation that we're gonna use so in order to determine the equation of that tangent, once we have the gradient for that equation, once we have the gradient of the tangent, we can now use this equation of the tangent, to determine, we can use that equation to determine the equation of a tangent, and then m will be the gradient that we'll calculate using what? Using the derivative, and then x1 and y1 are any point on the curve, any point on the curve, so now let's go ahead. Given the function f at x and the x value, so now we're determining the equation of a tangent. So the equation of a tangent can be determined, and the steps are just simple. To find the equation of the tangent, we need to find the y value first, and then the y value will use the original function that will be given. We'll use the original function which will be given the function of a curve. So we take the x value that will be given, and then we substitute that x value to the function, the original function that is given, to find the corresponding y value. And then to find m, the gradient of the tangent, we use the first derivative. Okay, let's quickly do this example to drive this point home. So we also find the equation of the tangent to the function f at x is equal to x squared minus x at the point where x is equal to 3. So first thing first, what do? We need to find the corresponding y value, and to do that we must use the original function that we are given here. So f at 3 is equal to what? Is equal to 3 squared minus 3. This would be 9 minus 3, which is 6. And then let's find the gradient. So we now have the point on the curve, which is 3 and 6. We have the point, the x value is 3 and 6, that is x1 and y1. Okay, and then next let's find the derivative of this function. So f prime x, the first derivative, is equal to 2x minus 1. Okay, now we have the first derivative of the what you call this thing. Sorry, we have the first derivative, of which we now can use to determine the gradient. So the gradient at x is equal to 3 will be f prime at 3 is equal to 2 times 3 minus 1, which would be equal to 6. Minus 1 is 5. that is the gradient. I can say m is equal to the gradient, and then from there let's determine the equation now of the the tangent at this point. At x is equal to 3, we're going to have y minus y1 is equal to m into x minus x1. Okay, what is y1? Y1 is, okay, I should have added a page. Let me see. Just gonna try to push this one a little bit lower. Yeah, I think here will be fine. Okay, we're saying y minus y1, which is 6, is equal to the gradient is 5 into x minus 3. Therefore y is equal to 5x minus 15 plus 6. Therefore y is equal to 5x minus 15 minus 6 will be minus 9. And there you have the equation of a tangent. Okay, and then let me see, next we have the point of contact. Okay, yeah, let's quickly do the point of contact, and then I will end this video, and then yeah, the graphical interpretation I will do it together with the cubic functions, Okay, so next, finding the point of contact. So the point of contact where the tangent and the curve meet, where the tangent and the curve touches. So if we are looking to find the point of contact, we will be given the gradient of the tangent. Let's say maybe m is equal to 5 or m is equal to whatever the number. These are the two steps that we follow to find the coordinates of the at the point of contact. So first thing first, we equate the derivative f at x, derivative of the function, to the gradient that we are given, and solve for the x value. Now remember that when we were looking for the equation of the tangent, we started by looking for the y value. Here vice versa, we're gonna look for the x value by using the gradient that we are given, and the first derivative of the equation. And then from there, once we have the x value, we have to use the original function to solve for the y value. Okay, so let's do this example to derive this point I'm making home. So given the graph of f at x is equal to x minus 2x squared, that is a tangent with a gradient of of 9, the tangent with a gradient of 9. Okay, so what's the first step? We equate the derivative of f at x, f prime x, to the gradient. Okay, and then we solve for the x value. So the first step A is to calculate, and we are looking for the coordinates. So f at x is equal to x minus 2x squared. And remember, we don't equate this function to the gradient, that 9 that we are given there. We only equate the gradient to the first derivative, because it is the first derivative that gives us the gradient, not the function. Don't make that mistake. Let's find the first derivative. So f prime x will be equal to 1 minus 4x. That's the first derivative, and then we take this first derivative, which also gives us the gradient. We equate it to the gradient that we are given there. So m is equal to, let's just say 9 is equal to 1 minus 4x. Therefore we're going to have negative 4x is equal to 9 minus 1 will be 8, divided by negative 4 on both sides, x is equal to negative 2. That's the x value. So, and then the second step, to find the y value, we must use the original function, this function that we're given here. F at x is equal to x minus 2x. Let's find the y value now. The y value, so f at negative 2 is equal to negative 2 minus 2 into negative 2 squared. This is equal to minus 2 into 4. This is equal to minus 2 minus 4, sorry, minus 8. This would be minus 10. Therefore, the point or the coordinates of the point is negative 2 and negative 10. Those are the coordinates of the point. And then next, determine the equation of the tangent we already have the tangent, which is 9, and we have the coordinates of the point, which is minus 2 and minus 10. So for B, we can use that equation of a tangent of y is minus y1 is equal to m into x minus x1. Okay, y minus, let's substitute, negative 10 is equal to, what is our tangent? We're given that it is 9, and x minus 2. Therefore, y plus 10, or let's take it to the other side, 9x plus 18 minus 10. Therefore, y is equal to 9x. 18 minus 10 will be 8 plus 8. That is the equation of the tangent. Okay, for now we will end this session here, and then for part 2 we'll take it from graphical interpretation of the derivative. We'll go into the second derivative, and we'll also do the cubic function. Yes, we'll also do the cubic functions, interpreting, solving for them, and sketching. And then we will also go into we'll also go in to doing past papers. Thank you for attending this session. I hope you gain some understanding from the session. I wish you good studying and good luck.